Hello YouTube. In this video we're going to introduce how one could necessarily find, say, the 6 trig ratios of an angle theta, but allowing theta to be whatever it wants. That is, in the past, if you've studied any trigonometry, then you know that when you evaluate, say, for an angle theta here, we'll put in a theta here, when we evaluate for, say, the sine, cosine, and tangent of this, we're often using SohCahToa, which involves our opposite side of the angle, our adjacent side of the angle, so the adjacent side, and then we have the hypotenuse side. It's just that in this instance, we want to be able to find the sine, cosine, and tangent of any angle, not just angles that happen to form up in right triangles. Because let's face it, when you think of a right triangle, which is where we use SohCahToa, the angles that are on the inside are kind of restricted. They are not able to be bigger than 90. That is, these two acute angles right here are both less than 90, and the biggest angle in the entire triangle is 90 degrees. So the hypothetical today now just becomes this. What if we were to have a triangle that had an angle, say theta, that was greater than 90 degrees? Or what if we didn't have a right triangle? Could we still find, say, the sine of this angle right here? And I tell you what, we can find the sine or cosine or tangent or any of those trig functions of this angle. It's just that we're not going to be able to do it with a right triangle, and so we can't use SohCahToa. So our efforts today are going to be to do this. Could we define a way to find, say, the 6 trig functions of this angle without having to use SohCahToa? And the answer to this is absolutely yes. So we're going to go ahead and introduce this by defining the definition of the trig functions in general. Okay, and so we say let theta be an angle in standard position. So let's go ahead and start by sketching our angle theta. Now this is just some angle that I'm sort of making up here. So let's go ahead and kind of in this space over here, let's make an angle in standard position, which we know means its initial side is on the positive x-axis, and let's just make its terminal side be here. We'll just call this our angle theta. But we say theta is an angle in standard position, and we'll let xy be any point except for the origin, but that is on the terminal side of theta. So what we're going to do is we're going to pick out some random point here. So for instance, if I switched over to like a green here, we say we just need some point xy, and we'll define xy as being on the terminal side of this angle. In order to find the 6 trig functions of this, what we're saying we need is just this, our angle theta and some point on the terminal side. But if we have a point on the terminal side, we could actually find all 6 trig ratios of this angle right here. And here's the reason why. If we had a point xy on the terminal side, what we can always do is this. We can drop what we call an altitude right back to the x-axis. Of course, the altitude of a triangle is typically referred to as its height. But what this does is it forms a right triangle. Okay. Furthermore, we say, well, do we know anything about this right triangle? And as a matter of fact, let's face it, if we knew this point right here, let's say we know this, say it was like the point 3, 4, I could tell you at least that this is 3 right here. It's gone 3 to the right and 4 up, which would allow us to kind of get some insight into the legs of this triangle. So what we're going to do is leave this not as 3, 4, but in general. But what we can say is this, if this is the point xy, then we have a triangle here that clearly has a distance from the origin out to this spot right here of x. And then we say, well, this would have a dimension of y. So just by knowing this point on the terminal side, we can actually form a right triangle in which we know 2 of the legs. The interesting thing here is this. If I know 2 legs on a right triangle, could we find the 3rd leg? And absolutely, we're actually going to give the hypotenuse of this triangle a name. We're going to refer to it always as r. Okay, and so it goes back to like radius of a circle. But for now, we're just going to call it r. But the simple fact of the matter is, well, if we had a triangle in which we knew the x dimension and we know the y dimension just by knowing this point on the terminal side, then we could drop down an altitude. As a matter of fact, use those 2 sides to find the length of r and then evaluate all 6 trig functions for this. So that's what I intended to do in the first place. I said, let's come up with a new definition for the trig functions. So for instance, if we were to find, say, the sine of theta, remember with SohCahToa, since we have a right triangle made out of this situation, we can use SohCahToa in that instance. But to find the sine to be opposite over hypotenuse. So in this instance, given this point xy on the terminal side, if we were to find the opposite over the hypotenuse in this case, what it means is this. Then we get the value y over r. As a matter of fact, if we were to continue with this, we say let's do the cosine. Cosine is adjacent over hypotenuse. If you look at your triangle that you formed up here, adjacent to our angle theta is this side x. and it'd be over this value of r, which is our hypotenuse value. And then last but not least, we have the tangent of theta coming out to be opposite over adjacent, TOA, opposite over adjacent of this angle. So we say the opposite side is y, the adjacent side is x. So we get y over x. And just to obtain the other three trig functions, which are cosecant, secant, and cotangent, all we have to do is recognize that these are just the reciprocals of the original three values here. So all we need to do is flip them over. So we get this as being y, or r over y. This would be r over x. And then last but not least, we would get this last value down here to be the reciprocal of y-axis, which is xy's. So this right here, this is the general definition of the trig function of an angle that's drawn in standard position. Okay. So a few things I want to say about this. First one is this. What this means is we can actually find the sine. Say if we were to go back and do it on this example that I had listed over here, if this was some angle in standard position, we could drop down an altitude here and evaluate the sine, cosine, and tangent of this angle just by using this right triangle right here. So essentially, we can find the sine, cosine, tangent of any angle so long as we know two things. One, a point on the terminal side, which we did, which allowed us to find the dimensions of this triangle, and then the hypotenuse, which we called r. So really quickly, before we proceed, I do want to define r. R is defined. R is the distance from our point, so from xy to the origin. That's what it is. Okay. So when we talk about r, we say it's the distance from this point here, xy, back to the origin. But we say, well, if I knew x and y, that is, I already know this point going into it, could we solve for r? And the answer to this is yes, we can. We could just use the Pythagorean theorem. So we know that the leg x squared plus the leg y squared equals the hypotenuse squared. If we're going to solve for r, we need to get rid of this squared. So what we'll do is we'll take the square root of both sides. That eliminates this squared. And we get this. We get r equals the square root of x squared plus y squared. Now I want to be clear on this. If r were the square root of x squared times y squared, we could just say this is xy. But since it's r equals the square root of x squared plus y squared, we can't just take the square root of both of these. But this right here, what I'd like to do is I'd like to go ahead and place that back up right next to this. So maybe we'll switch over to like, I don't know, like an orangey. But we say this distance back to the origin is defined as being the square root of x squared plus y squared. And the reason why this is important is because it allows us to always find r as long as we know some point on the terminal side. So I would like to put this into practice and kind of show what this would look like. But you'll notice here that I've listed all 6 trig functions defined thusly with an x and a y and r. And I've also written out the value of r as being the square root of x squared plus y squared. So why would this definition be so good when it comes to evaluating trig functions of an angle? Because it allows us to do any angle so long as it's sketched in standard position. All we need to know is a point on the terminal side. We just need some point. Okay. So as an instance of what this might look like, let's take a look at example 1a. It says, use this information of the trig functions in order to find the 6 trig functions of the angle theta, given that the point -3, 4 lies on the terminal side. Okay. So the first thing we want to do is we want to sketch this situation out. So we know that our angle is in standard position. We do know this. As a matter of fact, the only other thing I know about my angle is this. The point -3, 4 is on its terminal side. So if we were to sketch in, say, this point -3, 4, that would be like -3, go left 3, and then go up 4, 1, 2, 3, 4. What this means essentially is this. Our angle that was drawn in standard position, which means it started over here, its terminal side goes through this point right here. So we want to start by saying, well, first of all, this is our angle theta. Whoa, definitely not a right triangle, okay? So in order to make a right triangle out of this situation, this point -3, 4, what we're going to do is we're going to drop down in altitude. And what I would like to do is I would like to label the sides of this triangle. So for instance, we know that this leg down here is actually, we're going to call it -3. That's our x value. And we're going to call this 4. The only thing we're missing right now is this value of r. Okay, so we would actually have to go back and find the value of r. And we'll do so. But the simple fact of the matter is this. I want to find all 6 trig ratios of this angle theta. And according to my definition right here, all I need to know are 3 things. The value of our x, the value of our y, and the value of r. So what we're going to do is we're going to identify a few things. First of all, the x value of this point happens to be -3. The y value of this point happens to be 4. And the r value. Now here's where we're going to employ our Pythagorean theorem. Of course, I could write this negative 3 squared plus 4 squared equals r squared, and that would be appropriate. But we say in general, all we have to do is say, let's take the square root of x squared plus y squared, where our x value is negative 3, our y value is 4. So we would get r as being the square root of really 9 plus 16, which is the square root of 25. And what I'd like to point out is this. We're going to call this just 5. In the past, if you've taken an algebra class, you know that when you take the square root of a number, you get plus or minus. But for our purposes here, what we're going to write is this. The value of r is always positive. This is always true. So we may have a negative x value. As a matter of fact, we do have a negative x value right here. We may have a negative or positive y value. It happens to be positive for in this case, but r will always be positive. But since we've got our x and our y and our r, the simple fact is we can just go up here and use our definition of the trig functions to find all 6 of these. So for instance, if I want to find the sine of theta, we formally define this on the other page as being y over r. And in this case, our y value is 4. And our r value is 5, okay? If you were to go over here and look at this triangle in this case, we'd say it's kind of like saying opposite over adjacent is 4 over 5, okay? So we did just kind of find the sine of this right triangle. Let's go ahead and proceed with the rest of these. So we say the cosine. The cosine of this angle would be x over r, looking at our definition over here. So if sine's y over r, cosine's x over r, and so we say our x value of this point, we saw right here was negative 3. Negative 3 over our r value, 5. So before we go ahead and find tangent down here, I do want to point one thing out. That for the very first time, you're seeing probably that this is a negative value. And that's okay. You can have a negative trig value. It's just, it was because of this negative 3 in our x value here. Okay, so last but not least, tangent. We say tangent by definition is just y over x. So we could just take the y value of our point on the terminal side, we'll call this 4, and divide by the x value of the point on our terminal side, which is negative 3. And so these would be our primary 3 trig functions right here. In order to find the other 3, we'll make it really simple on ourselves here. We'll just say the cosecant of theta then must be the reciprocal of the sine, which is 4/5, so we get 5/4. Likewise, we say the secant of this point, which is the reciprocal of cosine, is negative 5/3. You'll notice I put the negative on top. It's weird to call the denominator negative, but I do want to point out that if cosine's negative over here, then its reciprocal must also be negative. And then last but not least, the reciprocal of tangent, which is cotangent. We'll flip this over, we get this. We get negative 3/4. Okay, negative 3/4. So these are the 6 trig ratios of this angle, theta, right here, and all we needed to know was a point on the terminal side and the value of r. So we're going to do this again up here. As a matter of fact, I want to use the definition of the trig functions again, which are these things over here, in order to find the 6 trig functions of this angle theta, given that the point 5, negative 12 happens to be on its terminal side. Before we actually sketch out the image on this one, I actually want to start by just saying a few things, starting with this. Our x value of our point on the terminal side is 5. The y value of the point on our terminal side is negative 12. So now in this instance down here where I drew out the triangle, I could easily see that I could use Pythagoras to find the value of r here. Could I find the value of r without actually having to sketch the picture? And the truth is this: yes. As a matter of fact, r is always equal to the square root of x squared plus y squared. So for instance here, if I want to find r, we want to find r, we say it is the square root of, let's go ahead and drop in our numbers here, x squared plus y squared, where our x value here is 5, and our y value happens to be negative 12. So simplifying this, we get the square root of 25 plus 144 is our r value. Furthermore, we get the square root of 169, and in this instance, it's very nice because that comes out to be 13, okay? Sometimes we don't get perfect roots, but we do get this. Now that we have x, y, and r, check this out. We can actually just go ahead and find the sine, cosine, and tangent of this angle because those are the only values that we need in order to evaluate the sine, cosine, and tangent of an angle. So we say sine. Again, sine is the y value of our point over the hypotenuse length. So we get this. We say our y value in this case is negative 12 over the hypotenuse, which is 13. Furthermore, if we wanted cosine, cosine's also over the hypotenuse. We get x over r, so this will also be over 13, but it is the x value of our point over that 13. So we get 5/13. That is its value. And then last but not least, tangent. If I wanted the tangent of this, we say tangent is y over x. Y over x. We want to memorize these, okay? So our y value in this case is negative 12, and our x value is 5. Okay, so in order to find these other three, we're going to go ahead and find cosecant of theta. We'll flip this over. We get negative 13/12. We'll find the secant, which is the reciprocal of cosine, by flipping this over and getting 13/5. We'll find the cotangent of this angle by flipping this guy over and get negative 5/12. Okay, so these are the 6 trig functions. So now the last thing I said I wanted to do was actually sketch the picture, which should have been the first thing we did. But I just wanted to kind of show you that you don't always have to sketch the picture to use this definition here. But our picture, let's see, we had an angle. We said the point 5, negative 12 was on its terminal side. So what this means is we're going to start by sketching in the point 5, negative 12. So that would be something like this: 1, 2, 3, 4, 5, 2, 3, 4, 5. 1, 2, 3, 4, 10, negative 15. Okay, so negative 10, negative 5, and this is our 5 up here, just to show you the scale. But we say this point right here, which is, oops, negative 5/12, which would be right 5 down 12, not down 15. We say this is the point that is on the terminal side of our angle. So what does our angle look like here? Well, we say this is an angle in standard position, and as a matter of fact, we'd say this angle is going to be assumed to be clockwise or counterclockwise rotating, positive in nature. Okay, so we say, well, where's our triangle at on this? Again, here's all we need to do. Let's drop an altitude from our point on the terminal side back to the x-axis, and this produces our right triangle here. Furthermore, if we wanted to see where we were getting our values from, essentially what we were saying was this side here is 5 in nature, this side here is negative 12 in nature, and if we're going to call r the distance back to the origin, we say we got r to come out to be 13, but all we did to find this was actually use the Pythagorean theorem to figure that out. Okay, so yes, you should always sketch a picture, but this is the definition in general of how to find the sine, cosine, and tangent of any angle. So long as you know a point on the terminal side, and you can always find the value of r after that. Cheers.